Okay, so for part 2 of lecture 11, we are going to continue with sufficiency and this theorem. Okay, so this is the theorem, and we have that T of capital Y is sufficient for theta if and only if L, the likelihood function for capital Y, L little y, we write the vertical bar given theta to indicate that theta is a parameter of the distribution, can be, but here's the result, can be factored this way, can be factored as a product of two terms. So this may be not all clear from this, but we'll make it clear through the examples. Can be factored as a product of two terms, one of which is function of little y only through the sufficient statistic, and this term can include the parameter, and another term which can now be a general function of little y but may not include the parameter. Okay, so in other words, the factor that has the parameter in it can see y only through the sufficient statistic, whereas the other factor does not include the parameter, but it can be general in terms of little y. This notation here is just called the likelihood for y. And we'll see it for the rest of the course now. And this just means the joint PDF or PMF. And it's just a general way to write either of them. So it's the joint density or joint mass function. That's all it is. But it's nice to have one sort of way to write it sometimes. Okay, so let's do an example. Notice it's if and only if two. So the factorization exists, then you know T of capital Y is sufficient for theta. Anytime this exists. So you can see right away probably, or you will once we start doing the examples, that there is more than one sufficient statistic. Also, if you know it's sufficient, you know you can decompose the likelihood in this way. Okay, let's do an example first. We will do proof for the PMF case. Okay, but first let's do some examples. So suppose we have y1, yn, say IID, say exponential, and say we use the rate for this. So then L just equal to the product of the PMFs. And we'll start using this indicator function to control the to control where the PMF or PDF is where this applies. In other words, densities especially typically have some part of the real numbers that is not too hard to specify, where they're zero, and another part where they're given by some formula. So it's convenient to use an indicator function. So we'll use this, and then we'll put the set where it is 1 down here as a subscript like this. So it's 1 from 0 to infinity. You don't need to include the 0 really, but we'll include it. And here I'll put phi I. So that just means this function evaluates to 1 if yi is greater than 0 and to 0 otherwise. Okay, so this is it. And we can do this now. What do we get? We get lambda to the n. E to the minus lambda can factor, and I get the sum yi. And for this, well, I think I can just leave this the way it is. I could leave it the way it is. One thing is I could also simplify this by replacing the product with, because the product would be applied to this. I can just put in the minimum here, because if the minimum is in this set, then all the terms are in this set. It's a little cleaner. So let's write it like this: 1. And we'll put the little order statistic notation that we have here. Okay, so it worked, right? And we see the sufficient statistic. So this term is G of just one factor, and right, so I got a factor with the parameter, and now I see that the sum is sufficient. And then over here I have H, and this is the whole sample. I mean, it's not, in this case, the whole sample, but it's a general part of the sample that doesn't involve the sufficient statistic. So it has to be separated out and not include, the main thing is it can't include lambda. Okay, so by the theorem, and we'll call this the factorization criterion, the sum, and now replace it with the capital YI, because this is the right thing to do, because yeah, because this is a function of the random variables. So this is sufficient. All right. Okay. Let's do another one. Well, if I know the sum, it's all the information about the rate that I can get from the sample. It's interesting. Something to think about. Okay. Example 2. Suppose we have again y1, yn, this time another continuous sample here. So say it's uniform 0 to theta. I don't know the right bound here. And we want to see what the factorization tells us. We're going to see that the max of this sample is sufficient for theta. So let's factor. We have L. In this case, it is theta, and this is the probability. This is the probability for each one. So this is just 1 over theta, and we'll use the indicator notation again. It's 1 as long as, yeah, we're in here, right? Okay, and the product goes from 1 to n. The constant comes out, that's nice. So we have theta to the minus n. And this product can be simplified, again, in a similar way. Right, I actually have 2 n terms here, right? I have n of these and n of these. When I remove the product here. So I have theta to the minus n. And I could do this kind of nicely by just going 1 and saying that the max has to be less than theta, right? The max has to be less than theta, or it's 0. So this is, write it like this. and the min has to be greater than 0, so I think you agree, right? And you see here you have G theta. Oh, I wanted to put the statistic first, right? G little y and theta. And over here I have H of y. Some general function that doesn't involve the sufficient statistic for H, but it also doesn't involve the parameter. So we're good on this one as well. Okay, do one more example for this part of for this video, and then we'll do a proof. So example 3. Now both the sufficient statistic and the parameter can be vector valued. So we will think of theta as, the parameter as a vector in R2, mu sigma squared. And turns out, yeah, we will see T is also going to turn out to be in R2. Okay, so let's maybe should we say that? Yeah, let's say show T of Y. And exactly what we want. Although there are certainly other sufficient statistics for this parameter or vector of parameters. This is a sufficient statistic. It's also unbiased, so we're going to show that this is sufficient for that vector. All right, so just a little more writing with the two things. So not let. All right. Okay. Am I going to make it? Yes. So, okay. What do we have? L. Okay. Another density. L. Product. 1 over. And exponential term. We do something we've done before with this now. Let's take this outside so we don't have to write everything. So if we take this sum here, and let's add and subtract y bar to it. So I get yi minus y bar. Let's see, I could also write it like minus mu minus y bar. So just adding and subtracting y bar to each each term in the sum here. So now I have this binomial thing, and I get the sum yi minus y bar squared. What else do I get over here? When I do this squared term, I get this squared. I'm summing it up. So I get plus n mu minus y bar squared. And for the cross term, it's 0, because the cross term just has the linear. It's linear in this term, right? And when I add this over all n, I get ny bar minus ny bar. So this is 0. So this whole thing is just this. Okay, you should convince yourself, if you don't believe me, that this is this. Okay, and so now we can substitute this back in. You notice that here I have y bar. I could even write this now like, we see this, if I divided this by n minus 1, I would have s squared. So this is the same as n minus 1, little s squared plus n mu minus y bar s squared, where we're just using the lowercase s squared and y bar to mean the, that function, the sample variance function of the observations, as well as the average of the observations. Okay, so L little y bar mu sigma squared is just equal to 2 pi sigma squared to the minus n over 2. And what's left is everything else. So I just have exp and then this sum. Am I going to be able to fit it? I think so. So in here I have okay, notice this whole thing is G, right? It's all there is. So this is G. I have my parameter and my sufficient statistics. So I have S squared and y bar. It's my T. And here I have my mu sigma squared and times h of y, which is just equal to 1 here, the number 1, right? So factorization criteria holds here, and we're done. So by FC, now I go to capitals, is sufficient. All right. Okay. I want to prove this now. And then just get into a little bit more application, and that will get to the next part. So I think we'll do the proof in a separate video. So I'm going to stop this.